For more than 3 decades, lithium-ion batteries have powered the modern world. They transformed mobile phones, laptops, electric vehicles, and renewable energy storage, becoming one of the most important technologies of the 21st century. Yet every technological revolution eventually reaches its limits. Demand for lithium is rising rapidly, mining costs remain volatile, supply chains are concentrated in relatively few regions, and concerns over safety, sustainability, and recycling continue to grow. Around the world, scientists and engineers are now searching for the battery that could eventually replace lithium-ion altogether. This is not simply a race to build a better battery. It is a competition to define the next generation of global energy. Lithium-ion batteries became dominant because they offered an exceptional balance between energy density, weight, rechargeability, and reliability. Compared with older battery chemistries such as nickel-cadmium or lead-acid, lithium-ion technology stored far more energy while remaining lightweight enough for portable electronics and electric vehicles. This combination fueled the explosive growth of modern consumer technology and the transition toward electrified transportation. However, lithium-ion technology is approaching a period of maturity. Engineers continue improving performance through better cathode materials, advanced electrolytes, and more efficient manufacturing. But many of the easiest gains have already been achieved. Increasing battery capacity without sacrificing safety, cost, or lifespan has become progressively more difficult. One challenge is the availability of raw materials. Although lithium itself is not exceptionally rare, extracting and refining it into battery-grade material requires significant investment, water consumption, and processing infrastructure. At the same time, many advanced lithium-ion batteries depend upon materials such as cobalt and nickel, which introduce additional supply chain challenges and geopolitical considerations. Battery safety also remains an important engineering concern. Lithium-ion cells store enormous amounts of energy within compact spaces. Under certain conditions, manufacturing defects, mechanical damage, or overheating can trigger thermal runaway, a chain reaction capable of generating intense heat and fire. Modern battery management systems have significantly reduced these risks, but researchers continue searching for inherently safer alternatives. This search has produced several promising technologies, each approaching the problem from a different direction. Rather than relying upon a single breakthrough, the future of battery storage may involve multiple chemistries designed for different applications. One of the most exciting developments involves solid-state batteries. Unlike conventional lithium-ion batteries that use liquid electrolytes, solid-state designs replace the liquid with solid materials capable of conducting ions. This seemingly simple change offers several potential advantages. Solid electrolytes are generally less flammable, potentially improving safety, while allowing engineers to increase energy density by using different electrode materials. Many automotive manufacturers and research organizations are investing heavily in solid-state technology. If successfully commercialized at scale, these batteries could provide longer driving ranges, faster charging, and improved durability. However, significant manufacturing challenges remain before widespread deployment becomes economically practical. Another rapidly advancing technology is the sodium-ion battery. Sodium sits directly below lithium on the periodic table and shares many similar chemical properties. Unlike lithium, sodium is abundant throughout the Earth's crust and oceans, making it potentially less expensive and more geographically accessible. Although sodium-ion batteries currently store somewhat less energy than the best lithium-ion cells, they offer several attractive advantages. Raw materials are widely available, manufacturing techniques resemble existing battery production, and performance at lower temperatures can be favorable. For stationary energy storage and certain vehicle applications, sodium-ion technology is becoming increasingly competitive. Flow batteries offer a completely different approach. Instead of storing energy inside solid electrodes, they use liquid electrolytes contained within external tanks. As the liquids circulate through the battery system, electricity is generated through electrochemical reactions. One major advantage is scalability. Increasing storage capacity often requires simply enlarging the electrolyte tanks rather than redesigning the entire battery. This makes flow batteries particularly attractive for supporting renewable electricity grids. Wind farms and solar installations require large-scale storage capable of balancing intermittent energy generation. Flow batteries may eventually provide long-duration storage measured in hours or even days, complementing faster response technologies already used within electrical networks. Lithium-sulfur batteries have also attracted considerable attention. Sulfur is abundant, inexpensive, and lightweight. In theory, lithium-sulfur chemistry offers significantly higher energy density than conventional lithium-ion designs, making it particularly interesting for aviation and aerospace applications, where reducing weight is critical. Researchers continue addressing technical challenges involving cycle life and long-term stability before commercial deployment becomes widespread. Metal air batteries represent another fascinating possibility. These systems use oxygen from the surrounding atmosphere as one of their reactants, dramatically reducing the weight carried inside the battery itself. Zinc air and aluminium air technologies have demonstrated impressive theoretical energy densities, although rechargeability and practical implementation remain active areas of research. Beyond chemistry, battery manufacturing itself is undergoing major transformation. Artificial intelligence increasingly assists researchers in discovering new materials by analyzing millions of possible molecular combinations far faster than traditional laboratory methods. Machine learning accelerates optimization while reducing development costs and shortening research timelines. Nanotechnology also contributes significantly. Engineers manipulate materials at atomic scales to improve ion transport, increase electrode surface area, and enhance battery durability. Tiny structural changes invisible to the naked eye can substantially improve charging speed, energy density, and overall lifespan. Recycling has become equally important. As battery production expands worldwide, recovering valuable materials from used batteries becomes both an environmental necessity and an economic opportunity. Advanced recycling techniques now recover increasing quantities of lithium, nickel, cobalt, copper, and other valuable elements, reducing dependence upon newly mined resources while supporting more circular manufacturing systems. Grid storage represents one of the largest future markets. Renewable electricity generated by wind and solar farms varies according to weather conditions. Reliable energy storage allows excess electricity produced during sunny or windy periods to be stored for later use when generation declines. Future battery technologies will therefore play a central role in stabilizing increasingly renewable electrical grids. Electric vehicles continue driving enormous demand for improved batteries. Consumers seek longer driving ranges, faster charging times, lower purchase prices, and greater durability. Meeting all four objectives simultaneously requires advances not only in chemistry, but also in manufacturing efficiency, thermal management, and battery software. Governments recognize the strategic importance of these technologies. National investments supporting battery research, domestic manufacturing, and supply chain resilience have expanded significantly. Countries increasingly view advanced battery production as an essential component of industrial competitiveness, energy security, and technological leadership. The race extends beyond transportation. Portable electronics, robotics, drones, satellites, medical devices, and defense systems all depend upon compact, reliable energy storage. Every improvement in battery performance creates opportunities across countless industries simultaneously. It is important to recognize that lithium itself is unlikely to disappear overnight. Existing manufacturing infrastructure represents hundreds of billions of pounds in global investment. Lithium-ion technology will almost certainly continue improving for many years, while serving applications where its characteristics remain highly competitive. Instead, the future will likely involve diversification. Different battery chemistries will serve different purposes according to their strengths. High-performance electric vehicles may adopt solid-state designs. Grid storage may increasingly utilize sodium-ion or flow batteries. Aerospace applications may favor lithium-sulfur systems. Industrial equipment may employ entirely different chemistries optimized for durability rather than maximum energy density. History suggests this pattern is common in technology. Steam engines did not disappear immediately when internal combustion engines emerged. Internal combustion continues alongside electric vehicles today. Similarly, future batteries are unlikely to replace lithium universally. Instead, they will gradually expand into applications where they offer clear technical or economic advantages. Perhaps the greatest transformation will occur quietly. Consumers may not notice whether their future devices contain lithium, sodium, or entirely new materials. What they will notice are products that charge in minutes rather than hours, vehicles traveling greater distances, renewable electricity available whenever needed, and energy systems operating more safely and sustainably. The battery revolution is therefore far from over. In many ways, it is only entering its most exciting chapter. Scientists are no longer asking whether lithium-ion technology can be improved. They are asking what comes next. The answer may not be one revolutionary battery replacing every lithium cell on Earth. It may instead be an ecosystem of specialized technologies, each solving different challenges while collectively powering the next generation of civilization. From solid-state breakthroughs to sodium-ion innovation, the future of energy storage is becoming broader, smarter, and more resilient than ever before. The technology that eventually succeeds lithium may already exist inside research laboratories today. Its commercial arrival could reshape transportation, renewable energy, artificial intelligence, and global industry for decades to come. Just as silicon transformed computing, the next great battery breakthrough may define the future of human progress itself. If you enjoyed this deep dive into the forces shaping our future, be sure to explore our other documentaries examining the technologies redefining modern civilization. And if you want to keep exploring the biggest questions about science, power, and the future of humanity, make sure to subscribe to the channel and join us for the next journey into the unknown.